What happens when black holes collide? Black holes are among the most mysterious and extreme objects in the universe. For decades, their bizarre properties have captivated scientists and space enthusiasts alike. For a long time, black holes were considered nothing more than a mathematical curiosity, so strange that even brilliant physicists doubted they could exist in reality. Today, we know they're real. Thousands have been detected, yet each one still holds secrets, and with every new observation, we get closer to unlocking them. In the past, studying such distant phenomena was limited to theory and imagination, but science has come so far that we can now not only observe black holes, we can simulate the most extreme events happening around them. On September 2nd, 2020, scientists recorded one of the most powerful events in astronomical history, the collision of two black holes. While similar mergers had been seen before, this one was the most massive ever detected. It happened 7 billion years ago, long before Earth even existed, at a distance of 7 billion light-years from us. The signal was named GW190521. One black hole weighed about 85 times the mass of our Sun, the other around 66. When they merged, they formed a new black hole of 142 solar masses, and the equivalent of nearly 9 suns vanished in an instant, converted entirely into energy in the form of gravitational waves. The signal lasted less than 1/10 of a second, yet it was picked up by the LIGO and Virgo detectors. Despite its brevity, it delivered a treasure trove of information about the nature of spacetime and gravity at its absolute limit.
So, what exactly is a black hole? In modern science, it's a region of space-time where gravity is so intense that nothing can escape it, not even light. Matter? Absolutely not. Describing it mathematically is incredibly complex. Near a black hole, space-time is warped to the extreme. The laws of physics, as we know them, break down, and reality behaves in ways our minds can barely grasp. For a long time, black holes existed only on paper, first as a mathematical oddity, then as a hypothetical cosmic object. They were nearly impossible to find. How do you see something that emits no light at all in the endless darkness of space? But nature leaves clues. A black hole reveals itself through indirect signs: a glowing accretion disk, a swirling storm of superheated gas and dust orbiting around it, and gravitational lensing, where its immense gravity bends the light from stars behind it, like a cosmic magnifying glass.
The first hint that black holes might exist came all the way back in 1784, when British scientist John Michell proposed the idea of dark stars, objects so massive that even light couldn't escape them. But it took nearly 2 centuries before we found real proof. In the early 1970s, astronomers discovered a powerful X-ray source in the constellation Cygnus, Cygnus X1. This became the first confirmed black hole. Today, we've identified over 1,000 black holes, and on April 10th, 2019, humanity saw something extraordinary: the first ever image of a supermassive black hole, the shadow of a cosmic giant at the heart of the galaxy M87. A theory born on paper had finally become observable reality. Like stars or planets, black holes can also come in pairs. 2 black holes orbit a common center, slowly spiraling closer together like dancers in a cosmic waltz, losing energy through gravitational waves. Eventually, they collide and merge into a single object, but the new black hole's mass is less than the sum of the 2 originals. The difference vanishes into space as a burst of gravitational energy. Such pairs often form when galaxies collide. For example, in the galaxy NGC 1128, located in the Abell 400 cluster about 300 million light-years away, lies the famous system C375, 2 supermassive black holes locked in orbit around each other. The galaxy's unusual dumbbell shape is likely the scar left behind by the merger of 2 elliptical galaxies, each once hosting its own black hole at the core.
An even rarer sight is the trio of supermassive black holes at the heart of galaxy NGC 6240, located just 400 million light-years from Earth. Two of them, together weighing about 1 billion times the mass of our Sun, orbit each other at a distance of 645 light-years, with one being 9 times more massive than the other. The third black hole sits farther out, about 3,000 light-years from their shared center, and has a mass between 240 and 420 million suns. This system is the closest known triple black hole system to Earth. A similar pair exists in the spiral galaxy NGC 3758, 425 million light-years away, where two black holes are separated by 110,000 light-years. Most other known systems lie even farther, beyond 500 million light-years. But here's the key point. Even when black holes get close, they don't always merge. It all depends on their masses, speeds, and the angle of approach. Under certain conditions, they can simply swing past each other, slightly altering their paths, like two predators in the night deciding not to fight. Astronomers call this elegant maneuver the gravitational dance. The actual merger process remains poorly understood. Its mathematical description is one of the toughest challenges in theoretical physics, full of gaps and approximations. Supercomputer simulations can take years to run, and it's real observations like those from LIGO that help scientists test and refine their models. One thing is certain, when black holes do merge, they release an enormous amount of energy, equivalent to the explosion of billions of supernovae. Almost all of it escapes as gravitational waves. Every gravitational wave we've detected so far has traveled for billions of years to reach us, its energy greatly weakened along the way. Yet even this faint ripple carries secrets about the very fabric of the universe.
But what if such a collision happened right here in our own galaxy? Simulations show that during a merger, gas in the accretion disks heats up to billions of degrees and accelerates to nearly the speed of light. This produces intense bursts of ultraviolet and X-ray radiation. If such a source were close enough to Earth, our magnetosphere and ozone layer wouldn't stand a chance. Within minutes, the atmosphere would begin to break down. The planet's surface would be scorched by invisible but deadly radiation. Most likely, all surface life would be wiped out. Only a few hardy microbes hidden deep underground or in the ocean trenches might survive this cosmic apocalypse. And that's not all. A powerful burst of gravitational waves could pass straight through Earth, shaking the mantle and triggering massive crustal fractures, chains of mega-earthquakes, and widespread volcanic eruptions, as if the planet itself trembled from a ripple in space-time. So what happens to the black hole itself after the merger? At first, it's not perfect. Its shape is stretched, like a droplet, or distorted, like a bell just after being struck. It rings, emitting final gravitational chimes, slowly losing energy. Over time, these vibrations fade, and the black hole settles into a perfect sphere. Then it continues to grow, pulling in gas, dust, and even stars, forming a new glowing accretion disk. It might even collide again someday. But eventually, everything nearby will be consumed, and then its growth will slow, and finally stop. Yet even black holes are not eternal. As Stephen Hawking showed, they slowly evaporate, emitting tiny particles right at the edge of the event horizon. This is Hawking radiation, the quantum whisper of darkness. Because of it, every black hole has a temperature, and the more massive it is, the colder it gets. For example, a black hole with the mass of 6 suns has a temperature of about 10 to the -8th Kelvin, almost absolute zero. That's why supermassive black holes evaporate incredibly slowly, so slowly that their death won't come until timescales far beyond anything we can imagine. The estimated lifetime of supermassive black holes exceeds 10 to the 100th years. That's a 1 followed by 100 zeros. This number is called a googol. As long as a black hole's temperature is lower than the temperature of the cosmic microwave background, which is about 2.7 kelvins, it absorbs more energy from the surrounding space than it emits. But the universe is expanding, and the cosmic background radiation is slowly cooling down. Sooner or later, every black hole will reach a state of thermal equilibrium, and after that point, it will begin to lose mass. At first, very slowly, then faster and faster. Complete evaporation will take trillions upon trillions of years, but in the end, the black hole will vanish in a final enormous flash, leaving behind only a fading electromagnetic pulse that gradually dissipates into the void. When the last black hole in the universe completes this journey, the era of eternal darkness will begin, an endless expanse of emptiness, cold, and silence. That will be the true end of the universe. Subscribe to the channel. It's only going to get more fascinating from here.